here's the part that's hard for us. The part that's hard for us is that we've known about atoms since, well, I don't know, middle school, elementary school, before that. I mean, my daughter's almost 5, and we talk about, the whole world is made up of little tiny pieces that vibrate. She knows that now. You've known that for a long time. So it's really hard to put ourselves in the shoes of people who did not know that. But there was a time when, of course, the nature of matter was a mystery. And the very earliest ideas about matter come from the Greeks. And really the very earliest ideas about a lot of the universe and things that we would start to call science today come from the Greeks. So Democritus was an early Greek philosopher. You will find slightly different years of birth and death for Democritus. 460 to 370 BCE are about the best ones that I found. They're the ones that seem to be replicated the most often. And what Democritus did was engage in sort of a thought experiment. So you should understand, first of all, that the Greeks that we're talking about are not scientists. Do not make that mistake. They are philosophers. This is like a couple of punch-drunk, sleep-deprived 19-year-olds on a random Thursday night in the middle of the night at Denny's on their 5th pot of coffee talking about the nature of the universe. They're thinking big thoughts. They have no evidence to back up their thoughts. There's no scientific process here. There's no observation and data collection and hypothesis and testing. This is thinking. And some of them thought some pretty good big thoughts. So Democritus imagined if you took a lump of lead, I think was what he talked about, but a lump of anything, and you cut that lump in half, and then you took one of those halves and you cut that in half, and you took that lump, one of those halves, and cut it in half, and you kept cutting this in half, that you would eventually get down to a unit of that material, of lead or of gold or of whatever, that couldn't be divided anymore, that was indivisible. And he used the term atomos, which was from the Greek for indivisible, to describe this tiniest piece. Now, you would not recognize what Democritus proposes as atomos. You may have come across pictures of them in your rambling research across the wilds of the interwebs, but he believed, and remember, this is belief, this is not any kind of real scientific anything, that they would have different shapes, that the characteristics of the materials were imbued by the shape of this atomos, this indivisible particle of which they were made. So some of them had little hooks, because they stuck together, they stuck to other things. And some of them were smooth, and some of them were triangular, and some of them were round, and some of them were, these crazy geometric shapes. Again, this has no basis in actual science. This is thinking. This is philosophy. But he gets credit now because it's the first time that someone proposes the idea that, in fact, there is some indivisible piece of matter for every type of matter that we know of. And he's thinking in terms of types of matter. So he's thinking in terms of lead and iron and gold and water. These are things that we know there are no atoms of water. You've always known that probably, or you've known it for a long time. So it's hard to step back and think about a point when this was really an unknown. So Democritus has these ideas, and again, only philosophy, absolutely nothing whatsoever to back up these thoughts. And, the person who shouts the loudest or publishes the most gets the most attention. So while a whole lot of people don't know Democritus's name, many people know Aristotle's. So Aristotle comes along a little bit later, 384 to 322 BCE, and you notice there are no publication dates or dates of research with these guys. Again, they're not scientists, they're philosophers. They're philosophers. And Aristotelian philosophy made a lot of impact Aristotle had many students. He wrote great treatises that survived. So we know about Aristotle. But most of his stuff sounds, how do I put it delicately, completely whacked to us. So he completely dismisses Democritus's, again, philosophical assertions about the nature of matter. They are philosophical assertions. They are not science. And there are other earlier bodies of work that talk about the four elements. And these are not elements in the sense that you or I think of elements. These are the elemental forces of the world: fire, water, earth, air. And these are very old, really religious ideas and philosophical ideas. He says matter is continuous, meaning there is no individual unit of matter. There are no little pieces. There are no units. And Aristotle's a pretty convincing guy. Have you ever known somebody who was wrong but who yelled loudly enough that everybody believed them? Me too. Aristotle's views, his ideas about the nature of matter take hold. And for the most part, the ideas of Democritus, and there's a whole school of thought of other people who had studied and taught and worked with Democritus, and they're called the atomists. I'm saying that not without more coffee. Their views kind of get left in the dust. And this Aristotelian notion of everything being made of the four elements and matter being a continuous thing ends up really kind of holding sway. So this is where you get things like medicine at this time. Oh, your humors are out of balance. You have too much fire and not enough water. Hence, you have a fever. Huh? You know, you need more earth in your constitution. Eat this dirt. I'm not kidding. It sounds insane to us. I mean, it sounds really seriously, clinically insane, and it sounds like it would kill you. Yeah, it did sometimes. Oh, there's too much water in your constitution. We should get rid of some of your blood. Bleeding people to balance their humors. Bat poop crazy. But this was the thinking of the day. And, you know, in terms of the PR campaign, in terms of the war of ideas, Aristotle won. Okay, this is the idea or the concept that I think confuses most people in this project. But I wanted you to come to it and explore it and find what you could on it. Alchemy. Alchemy is a school of thought. It's not an individual. It is a school of thought. There are people who will call alchemy sort of the predecessor of chemistry. Well, it is and it isn't. The alchemists' ideas were, again, philosophical, not so much scientific. But they were also magical. They were also religious. So they were looking at this within a context of a whole lot of things that we would not describe as science. And what the alchemists believed was that they could take materials found out in the world, lead, iron, clay, water, and they could manipulate them because these things they believed were made of the four elements, the earth, the air, the fire, the water, and that by performing various acts upon these materials, they could change things into gold. They believed they could transmute base metals into gold. One of the big ones that they focused on was lead. And so they heated stuff up, and they boiled stuff, and they burned stuff, and they did all sorts of interesting things. They did actually contribute to modern chemistry. So you have all benefited from something that is an alchemical contribution, and that is distillation. If you have driven a car or any other device powered by an internal combustion engine, the raw crude oil that comes out of the ground is not what's powering your car or your dirt bike or the bus you rode here on or whatever. It is a petroleum distillate, which means that crude has been taken, heated to various temperatures so that various components of the crude would come off and then be condensed. Distillation processes are sort of a gift of the alchemists, which makes it sound very romantic, doesn't it? A gift of the alchemists. But yeah, they did. They made contributions. A lot of our modern chemical glassware actually was developed in these alchemical labs. And, I use lab in the loosest sense of the word. These people would have been making their own glassware. They would have been making all their own apparatus. The sort of classic image of the lab with bubbling potions and dripping who knows what very much harkens back to this alchemical idea. So these alchemical ideas, this sort of school of thought of alchemy, starts in ancient Greece. It starts with these Aristotelian notions. But it gets developed sort of worldwide. There are major centers of alchemy in the Islamic world, in the Middle East, in North Africa, in parts of Asia. There's a strong Chinese school of alchemy. And when I say school, I don't mean a physical building where people go and they study alchemy. I mean school of thought. So there are people working on these alchemical ideas. And it continues to evolve in medieval Europe. And so it's this sort of worldwide, this is how people are thinking about matter. But again, it's all rooted in that crazy, wacky Aristotelian stuff. I say alchemy is starting to stretch towards science because you have this idea of experimentalism. We believe this will happen. And it's not formal. It's not, here's our hypothesis, let's test it. But we believe this will happen here. Here's how we will do it. So it begins to be this idea of taking a philosophical idea and putting it into physical practice. And that's something the Greeks didn't do. Democritus had no equipment. Aristotle had no equipment. They're just thinking. The alchemists, at least, are starting to translate that thought into action. Time passed. So we have these people playing crazy alchemical games and distilling all sorts of things and dropping lead into acid. Time passed. Oh, it sure did. Civilizations rose and fell. The Romans, for instance, the entire Roman civilization, hundreds of years of colonization and all sorts of other interesting things. Let's see. The Celts swept across Europe, invaded the British Isles. Then the Romans came. My head's in the British Isles right now because of what I've been reading this summer. Then the Romans came. Then the Romans left. Then the Saxons came. All during this time. Not to mention all the things going on in China, going on in Africa, going on in North America, the Iroquois Confederation, yeah, all this. Civilizations rose, civilizations fell. Time marches on, and you know what? We're still stuck with some crazy stuff. Crazy stuff. It'd be fun to put together a timeline of all the things that happened while nothing much was happening scientifically. Nothing is happening in terms of matter and how people think about it. I mean, okay, don't get me wrong. They're distilling probably, some fairly high-quality liquor. But, because they've figured out distillation, they're, dissolving chunks of metal in acid. They're getting interesting things. But they're really not getting anywhere. Like 1,500 years. Now, mind you, we have to remember what life is like for the masses during this entire period. If you're lucky enough to not be born a serf or a peasant or somebody who's basically going to struggle to get enough calories to survive for your entire life and maybe reproduce successfully and maybe see a few of those children grow up to reproduce. Also, you don't really have a whole lot of time to think about matter. You have a whole lot of time to think about the wheat crop and mold on all of your food and staying warm and not freezing to death or having your children freeze to death. And if you are born to a higher strata of life, because at this point life is very stratified, you're probably mostly thinking about repelling invasions or invading somebody else's territory. there's not a whole lot of scientific thought going on here. People are a little bit preoccupied. And so the people who are doing anything that we might even approach to call scientific thought are stuck in this alchemical notion and these Aristotelian ideas, which, frankly, though as I said, they did give us distillation, aren't all that helpful. Aren't really explaining the world in a scientific way. We're not thinking in terms of observation and data and hypotheses and testing them. We're just not there. It's not where we are. So then something happens. And I think there are a few names that you probably came across, but were not on your rubric, like Lavoisier and Proust, possibly Boyle. So between about 1770 and 1790, this roughly 20-year period, largely in Europe, we have what's often called the chemical revolution. And Antoine Lavoisier sort of spearheads this. He's young, he's smart, and he thinks a lot of what he's taught is kind of bogus. It's good to question what you're taught. I could be giving you bunches of nonsense right now. You have to trust that I'm not. I'm not, I promise, this time. Not that I wouldn't do that sometime, but I'm not doing it now. So Lavoisier, there are some crazy ideas. Still, people are starting to try to think scientifically, but they're not doing a great job of it. There is this idea, because people have been burning things for a long time, and it has been noted by people who are doing any kind of experimental work that some materials seem to gain weight when they're burned, and some materials seem to lose weight when they're burned. How do you explain that? So at least there we have the beginnings of an observation and a question being asked, and then seeking an explanation for these observations. And the dominant theory of the day is something called phlogiston. I'm probably not pronouncing that correctly, but it's supposed to be this mysterious material that all things contain. And it's the part that burns. And so the weight gain is a gain of phlogiston. Phlogiston is like something in the air, but it's what's needed for burning. And I don't even completely understand it. I don't think I can, as somebody who never believed this stuff. I'm not sure I can completely understand where it was coming from. But it's this mysterious stuff that's in the air around us that's contained in some materials. Well, Lavoisier thinks this is kind of bogus. And he undergoes a series of experiments in which he basically burns a lot of stuff. And he does all these combinations. He burns things in closed vessels. He burns things in the presence of just everyday air. And what he begins to believe is that, in fact, air is composed of two different things. And, in fact, when you're burning things, he begins to believe that air is something that contributes to burning, and that there's some piece of air that ends up getting added to other materials. And this is actually revolutionary. You wouldn't think it is, because we know that, obviously, there's oxygen in the air, and things don't burn without oxygen. But nobody knows this. So he burns things. He measures this gain of mass, and he proposes that, in fact, air is made of a couple different pieces, and one of these pieces is flammable. And then it combines with other things. All of this leads him to propose what's called the law of conservation of mass. We'll talk a little bit more about it in a second. We also have the law of definite proportions, and this comes out of some of the same kinds of work. Proust proposes that every sample of air, every sample of water, every sample of water, for instance, has two different parts, and that they're in the same proportions, no matter where that water comes from, if it's pure water. That every sample of any material has the same proportions. And then we get Dalton's law of multiple proportions, which we'll talk about. That's the least obvious, and we may do sort of a mini lab on that tomorrow. We'll see. This is quantitative chemistry. What does quantitative mean? Quantitative data is numerical data. Part of this revolution is possible due to instrumentation. The kind of balance that we have, and I have had students complain about the balances that we've got, the triple beams. The kind of balance that you've got is so many light years ahead of what would have been available to someone in 1750 or 1700 or 1600. The kind of precision instrument that you've got here is light years ahead of what would have been available to Lavoisier. Light years. Part of this revolution is made possible because suddenly the instruments are available. People can make better quality instruments, and people are capable of making precision measurements. So this idea of precision really underlies a lot of this. And I am going to mention one other thing. This is what I call the rich white guys tinkering around in their basements era of chemistry. So, again, I've been reading, fiction set in the British Isles through the Saxon invasions and the Danish invasions and pre-Saxon invasions and Roman Legion era all summer. And it's nice to consider for a moment what life was like for people. Primary considerations for the majority of humanity during all of that time: not starving to death, not freezing to death, not being hacked to death by invading whoever's, the invader of the week, looking for your food so that they wouldn't starve to death, and just basically not dying every single day. Primary consideration. So who has the time and the liberty and the energy and the space, sort of the mental and emotional space to think about matter? The very wealthy. A tiny percentage of the population who's not just worried about not dying every day, who's not worried about making sure that the wheat harvest is in, who's not worried about keeping rats out of the grain bins. It is a tiny percentage of the population, and they're people who are playing with their family's money, collected, I might say, off the backs of the people who are worried about not starving every day. But that's who can do this. So it's rich white guys tinkering around in the family's estate's basement, in the basement of the castle, metaphorically. It may or may not really be a castle. But it's a tiny little percentage of the population. So we're not making a whole lot of progress because a lot of humanity is not at this point freed up to think about anything beyond just mere survival. Law of conservation of mass. I like the cartoon. You can see it's a little outdated, but I think it's kind of true. You can't create or destroy mass in an ordinary chemical reaction. You can't create or destroy mass in a physical change. Mass remains unchanged. Burning is, of course, a chemical reaction. A lot of this comes from Lavoisier's work, where he was burning samples of charcoal, samples of magnesium in closed vessels. Closed vessel combustion. And if you account for the mass of the air that's in there, does the mass of the magnesium change? Yeah, it does. But the mass overall does not. Stuff has just traded dance partners. Mass is not created or destroyed. Interestingly enough, you know what ended Lavoisier's career? La guillotine. He had his head cut off. The French Revolution. He was nobility. Again, who had the opportunity? Who had the sort of freedom from, ironically, freedom from fear of not dying every day, to think any kind of deep thoughts about matter? The nobility, the wealthy, and of course during the French Revolution, many nobles suddenly found that fear of, that whole thing about not dying every day to be rather complicated by Monsieur Guillotine. And someone commented after Lavoisier's death that it took but seconds to sever that head from that body, but not in 100 years shall we see another head like it. So one of those sort of tragedies to science. Who knows what else Lavoisier would have thought up had his head not been severed from the rest of his body. But it was, sadly. Okay, so this is Proust. And the law of definite proportion says that a chemical compound has the same elements in the same proportion. Doesn't matter how much or how little you have. So we can take 1 milliliter of water and we can split it into proportionate amounts of hydrogen and oxygen. We can take a liter of water. We can take a kiloliter of water. And no matter what, the proportion of oxygen to hydrogen will always be the same. Is it 11.2% 11.2% hydrogen by mass, 88% oxygen by mass? It's something like that. Always. No matter where the sample comes from, no matter how big the sample is, no matter how small the sample is. We could take my lovely, well, that's a bad example because it's very impure. We could take this lovely and much purer sodium chloride. I'll clean it up, I promise. We can take that sodium chloride. Doesn't matter where it comes from, doesn't matter how much we use. We can always separate this into 45% sodium, 55, I'm forgetting the exact numbers, but a given percentage of sodium and chlorine, no matter how big or small the sample, no matter where the sample comes from, as long as it started off as pure sodium chloride. Doesn't sound revolutionary to us, but that's starting to point to something. That is starting to point to something. Now, the third one is the one that's hardest to understand and think about. Who here feels like they have a complete grip on the law of multiple proportions? I don't think your book does a great job with it, though the pictures help. I had been teaching this content for several years before I felt like I really understood law of multiple proportions, even a little bit. So this is proposed by a man named John Dalton, and he sort of starts to break the mold in that while Dalton is certainly from a comfortable middle-class kind of world, he's not the kind of minor nobility we've been seeing up to now. He's a school teacher. I mean, which in England at the time, and we're talking late 18th, early 19th century, certainly meant, he was no serf. He was no, as my dad would have said, a dirt farmer, because my parents were dirt farmers. Dalton is sort of a step up that ladder, but, he does represent a break with the idea that only nobility has time to think about this, or the energy, or the intellect. So the law of multiple proportions. If two or more compounds are composed of the same two elements, then the ratio of the masses of the second element, Gesundheit, combined with the certain mass of the first element, is always the ratio of small whole numbers. Does that make any sense whatsoever to you? Because I can read that about 10 times, and it doesn't compute. The first step is admitting that. The first step is admitting that really doesn't help. The words don't help. So we've got this bunch of words that don't make a whole lot of sense, proposed by John Dalton, English school teacher. So let's see if we can break this down a little bit into something that's a bit more sensible. Yeah, huh? Because it doesn't make a lot of sense when you read it. So carbon dioxide and carbon monoxide. One of them you breathe out. The other one your car breathes out. If I park too close to the garage and I start my car in advance, sometimes I set off the CO detector in the garage, much to everybody's chagrin at 6 o'clock in the morning. So if we look at a sample of carbon monoxide, we can break that down into, if we look at we haven't talked about moles yet, but we look at 1 mole, 12.01 grams of carbon, 16 grams of oxygen. And after Lavoisier and Proust, they are starting to gain the ability to separate elements. And like I said, Lavoisier separated out oxygen. He actually named that because I just saw this. The name oxygen comes from the Greek, I believe, and it's like acid giver, because what he figured out was that many acids contained this mysterious element, which had been called flammable air. So, okay, we've got this sample of CO. We can separate it out. Well, if we take a sample of this other gas, which contains the same elements, and we separate it out, well, we get the same mass of carbon, but we get 32 grams of oxygen. And if we look at the ratio of oxygen in those compounds, we find that it's 2 to 1. And we find that we can look at any compound that has carbon and oxygen. And when we look at the mass of the oxygen against the mass of all those other compounds, it's always going to be a small whole number ratio. 3 to 5, 2 to 1, 3 to 2. And what that starts to tell us is that there are discrete pieces of this oxygen, discrete pieces, and that there are twice as many pieces of oxygen in the second compound as there were in the first. This is all good food for thought for Dalton, and we're going to pick up with Dalton tomorrow. Tomorrow, I'm trying to pull together a couple little mini labs to look at the concepts in these 3 laws, and then we will pick up with where Dalton took these observations. Questions, comments, concerns?